This conference will now be recorded.
Again, with Ensemble learning. Let's quickly recall what we did on backend. So like we said last time, that these methods are like Ensemble methods. They generally beat most models when it comes to competitions. Like you see here, if you go to Kaggle competitions and you open them, you open the competition and see what's on the leaderboard, especially for tabular data, like data that are not text or images. You will find some sort of Ensemble method winning. It's like probably more than 95% of the time. It's always ensembling, and especially gradient boosting method. We have talked about that. We have this trade-off, the variance bias trade-off. It's like, and this is a phenomenon that happens with most classifiers. It's like you can have a classifier or a method that has high variance and low bias, and vice versa. And what we want, both of them low. We want both of them to be low. A high bias means that the model is not learning well. Its accuracy on the training is not good. And the high variance means that a model is if you can call it overfitting. Like the accuracy on training and testing are different. So this is what we mean by high variance. The accuracy on training and testing are different. So here we have a high variance, as you can see. It's like the accuracy on training and testing diverge. But here the variance is low because they are almost the same. And the bias, here we have a low bias because the accuracy on training is very low, is very high, sorry. The error is low, but the accuracy is very high. So if we go this way, this is like happening in most models. If we go this way, we improve what? We improve the bias.
Yeah.
And then it means the accuracy on training is good, is getting better. It's almost 100% here. And if we go, but we are losing on generalization, which is, to be honest, useless. We want to generalize. We want both to be the same, to be like that on training and testing. We want them. And if we go that way, the accuracy is low on both training and testing, but they are similar. And we want the best of both worlds. We want something that goes that way. And this is what ensembling methods do. Some ensembling methods will improve the variance. We'll make like this and this similar. Some ensembling methods do this the opposite, which means they improve the bias, which means if we are here, this will go down. Both will go down. So of course, from this perspective, they will be used with different models. Like some models will work well with improving the bias. Other models will do better if we improve their variance. Do you agree with me? Like if you take a student that is good at memorizing, excellent at memorizing, do you approach him the same way to solve problems as a student who is good at detecting patterns, at making general rules? Do you improve them the same way? Will you improve how they are doing? It's not the same way that we want to improve these two guys. They are different. One student is memorizing perfectly, which means he's doing well on the training set, but memorizing won't help on the testing set. So we need many students to help him to generalize. Other students detect patterns well, but they detect very few patterns. Like they can generalize well, but they don't detect a lot of things, just few. So these guys, we are going to improve them. We need something different. I guess you are happy with this explanation. Can someone like just say if you agree or you want more explanation?
Once more, please.
Sorry?
Can you explain it again, please?
Sure. So what we have is like in most, like this phenomenon happens in most machine learning models. Some models, when they can have a high accuracy and a low generalization. It means they have a high accuracy on training and a bad accuracy on testing. Can we name one model that behaves generally like that? Where we notice this phenomenon happening. Well, what model can like have this?
Decision tree?
Decision tree.
Exactly, yeah. Decision trees have this aspect of them happening. Decision trees can have excellent accuracy on training, but they will lose it on testing. Like the bigger they are, the better they get here. They become more complex, and they lose accuracy on testing.
Okay.
This is for the large decision trees. Other models have the opposite aspect. They can go very simple if we go that way, but they lose their accuracy. However, their accuracy on testing is almost similar of their accuracy on training. It means that you can trust them with predictions.
Yes.
You can trust them.
Yes.
But you are not fully satisfied. You are not really satisfied. Here you are satisfied with the training, but you can't really trust them. If you go here, you can't trust them. So something we want to do is somewhere in here. Something in here is really good. Is good like compared to what we have.
Good compromise.
Yeah, good compromise. So this is a trade-off, like a compromise, where we need a model that is just complex, like just enough to make a good accuracy and a good generalization, which means we go here. Ensemble methods, when we like introduce them to certain algorithms, to certain models, they can improve. We can like go a little bit that way, and like generalization will go better, will become better. For example, this red line will become something like that instead of a line like that. I will start to draw in. So if, for example, especially in bagging, decision trees are like that. But if we introduce bagging to them, we can end up with something like that. They improve what? Bagging improves what?
Variance.
Variance.
Yeah, which means generalization. They make the model general enough. So we use them with what kind of models?
Decision trees.
Decision tree. Big ones.
Complex ones, yeah. Decision trees with a large like depth. So that's why when we use, but not necessarily just decision trees, we can use them with multiple algorithms. There is no like reason like to lock them on decision trees. It's just that it is very common to use them with decision trees. And boosting does the opposite. It makes this, it goes here, and make them both like this. Improve both of this like that. So it makes like it use less complex models and make them more precise. And we are going to see how. So boosting, we will use it with what?
Small tree.
For example, a small decision tree, exactly.
Yeah.
And this is like the rule of thumb, how we use boosting generally. We use boosting with very small decision trees. Sometimes in one algorithm we are going to see with a tree depth of only one level. And when boosting it, like putting them in one, like using multiple small trees of one, we can get excellent results. Sometimes even better than Baggin. Are you fascinated, guys, with this? It's really impressive, almost magic. So this is what we saw last time, how Baggin works. Baggin, like we divide the dataset into multiple subsets. And in Baggin, do we have repetition or not?
Yeah.
Yes, we can have repetitions, like this one, or like, because we select things randomly. And when for example we do Baggin with decision trees, which is kind of the random forest, when we use random forests. What I was going to say. Yes, these trees are constructed in parallel or in serial. Like we construct these trees one by one, or we construct them independently.
Independently?
Yes, they are independent, because like we saw here, we are building the different sets. They don't know what they have. Each set is different, and for each set we build this mini decision tree. It's not like really mini; it's a big decision tree, but with that randomization inside.
Yeah, there should be no correlation. There should be no correlation between them.
Yeah, we just want them to be less correlated, so they will all be different randomly. So they are constructed all in parallel. So that's what happened in Baggin. Now let's go to boosting. With boosting, guys, we combine different general rules of thumb. With Baggin, you know what is a rule of thumb? Like, it's like a general rule.
Yes.
Something that is vague, that we learn by experience. Like when it is cloudy, it rains. Something like very vague, like that. Like the rule of thumb. So here we can see the difference with Baggin. With Baggin, we have like very precise rules, like very large decision trees. But here it's rather rules of thumb. And we have several of them. We combine them to make them into a highly performant model. So the method uses an algorithm that can find a classifier that generalizes very well. Accuracy on the testing is similar to accuracy on training. Of course, and the accuracy we want it to be acceptable, better than a random guess. So they generalize very well. Accuracy on testing on training are similar. This is the generalization, but their accuracy is just acceptable. They do just slightly better than a random guess. It's like if you have a binary classifier, they will make like 55% accuracy. So we call this type of classifiers weak classifiers. We call them weak. Combine in a way these weak classifiers to make a more accurate model. So unlike Baggin, boosting reduces the bias. That's what we were saying. We will be inclined of using models with low variance and high bias. So we want to improve the bias, which is the accuracy on training and testing. So models that have a similar performance score in training and testing, and that score is not good enough. That's what would be the base, generally the base model for boosting. A model that has a similar accuracy in training and testing, but the final score is not really good. Slightly better than a random guess. And also, unlike Baggin, where we construct the data sets like randomly, we divide them and we construct them randomly, these data sets, the subsets. In boosting, every new classifier will focus on the misclassified sample. So we still construct different data sets in Boosting, but they are dependent on each other. In Bagging, they are totally independent. Like data sets are constructed randomly in an independent way. But in Boosting, they are constructed sequentially. Like we construct the first data set, and then the new data set will be influenced by the mistakes that we made in the previous data set. And we continue like that. We are going to see how. So in Bagging is parallel, Boosting is sequential. So this is an example of boosting, of Adaboost. Adaboost adaptive boosting is one of the famous boosting methods. And it does very well. It's not the state of the art. The state of the art, we can call it the gradient boosting method, which is, I would say, quite close to adaptive boosting in some ways. So how Adaboost works? It constructs a strong classifier using a linear combination of several weak classifiers. And Adaboost also will generally use it with trees. Trees that are big or small?
Small.
Small, still small, exactly. So what we do, we take the data set in this Adaboost method. We take the data set. We build a model using a small tree. Then we see where this model did make mistakes, like what samples we got wrong. For example, sample 3, sample 4, we got wrong, sample 20. We see what samples we got them wrong. And then we construct a new data set that gives the samples that we got wrong more importance. You can do multiple things with them. You can give them like a weight. You can duplicate them. For example, if the sample we got it wrong, we duplicate it. We make more samples of it. So we will have more, it will influence things more. So it will give, this data set will give more importance to the samples where we made a mistake, where this classifier, where this model made mistakes. And then we construct a new model based on the new data set. So this model and this model will be different because this data set is different than this data set. Like samples are not the same, exactly the same. Here, some samples are made more important. And we do that again. We build again a new model and see what samples we got wrong again here. We give them more importance and send them back to here. So dataset 3 is also derived from dataset 2. And it has like the samples that model 2 got wrong, predicted like not accurately, will be given more importance. Again, this model will do the same thing, and we keep doing that. So we end up with a series of models. We end up with this series of models. When we have to stop at some point, well, when we stop, these models will vote. Like when we have them, this 10 models or whatever, how many models we have, and we want to predict some outcome for a new sample, this model will vote. Like we send the sample to all of them, but they will vote with a weight. They are not all equal. Their weight depends on how good they did, how well they performed on their respective data set. So the model that will have the higher vote, like more weights into his vote, will be the model that did very well with his respective data set. Are you happy how this works in a nutshell?
Yes.
Reda,
Uh-huh.
what do you mean by giving importance to misclassified data?
Yeah, there are many ways of giving them some importance. So we have here our data set.
Mm-hmm.
Here we have the class. There are multiple ways of giving them this importance. So if we are using decision trees and say that we model 1 got this sample wrong, it didn't classify it well, and got all of the other samples right. So how do we give this sample more importance? There are a few ways. We can just duplicate it. Like this sample, we duplicate it again and put it in here. So we have 2 copies of this sample. This is a simple way. Okay? There are other ways that we use a decision tree that has weights. It's not like a regular decision tree. Decision tree that associates weight with each sample. In the beginning, they are all equal. Their weights are all equal. 1, 1, 1, 1, etc. But if we want this sample to be different, we, for example, put its weight to 2. There is a proper formula for it, but this is just for the sake of an example. We put it as 2, and the decision tree will focus, we give it more importance when it is constructed. It's like it is we have 2 versions of this copy. So this is what we mean by giving a sample more importance. The model needs to consider that this sample is more important than the other samples. Okay? Are you happy, Amal?
Yes, yeah. Thank
Guys,
Eva,
are you happy?
can you repeat how we select the model? How we select the good model in the end?
No, we don't select one. We take them all. We take them all, not just one. We take all the models, and they vote when we want to classify. Yeah, when we want to classify a new sample that is coming in the future, we put that sample in all of the models, and they start voting. So this model will say it's class 1, this will say class 2, etc. And we take the majority, but we have a weight. So each model has like a different importance. They are all the same, but not all the same. So
Okay.
this model, like their importance is their how good they performed on their respective data set. So if this one got 90% accuracy, and this one got 70% accuracy on this, so this model will have more importance when we average things.
Okay.
Okay, are you happy?
Yeah.
Yeah.
It's good.
Can we? By using
So this is in a nutshell how adaptive boosting works. We are going to see now the details. So this is the algorithm. So this is the steps pseudo algorithm. So give an importance score to each data point sample in the training set. Initially, this importance score is equal across all samples. They all have the same importance. That's what we just said. Are you happy with this? Then use the training data to build a weak model. Generally, a decision tree with only one variable is used. This type of decision trees are called stump. It's like a very small tree with one level. It's called a stump. Compute the performance of the model built and determine what samples are misclassified. So we compute the performance of this stump, how many samples we got right. So this is the performance, and determine what samples are misclassified. So we determine, like for example, samples. If we have something like that, say we got this wrong and this wrong, so it will be. So we have here 4 samples. So we got 50% right, and 2 samples wrong. So here 2 samples are wrong and 50% right. So now we reconstruct a new data set by giving a higher importance score to the previous misclassified sample. So this one will be more important. Well, I will show you the formula. There is a proper formula to compute this and this. In the beginning, they are all the same. Their importance are all, say here, we have the importance here. So we have 4 samples. They will all be 0.5, 0.25, sorry. So it's like that. That importance will sum up to 1. 0.25, 0.25. So initially they are all like that. But after we made a mistake here and here, we want the next model to focus more on this and this, to try to get this right more. So the next model, what we'll have, we have the same data set, but with a difference in importance. So this will change, and this will change. And we repeat step 2, 3, 4. Sorry, I made a mistake here. 2, 3, and 4. So we go to 2, and we construct a new model. We compute its performance, what samples got wrong, and we reconstruct a new data set. So we are, at each iteration, we are creating a new model with different importance. So the samples will have, each time will have different importance. So the models will be a little bit different, or sometimes a lot different. The final strong classifier is the sum of the weighted result of each model. The weight of the model is based on the performance of the model computed in step 2. So the performance will determine its weight. How like say do we give him this? Do we give this model? How important is the vote? Some models will have a very important vote. Others will have lower, and this depends on their performance.
Reda, please, can you repeat the last point?
The last part, this.
Yeah, the class. Yeah, this one.
Yeah, when we built all the classifiers, we decided to stop, and we built like 10 classifiers. The final decision that we make on new samples, now when we build the classifier, we want them to make predictions on what is to come in the future.
Yeah, correct.
So how do we like combine them? We take this new sample, we put it inside every model. So every model will have a prediction.
Correct, yeah.
What will happen now, some predictions will be different. We are going to a voting system. Models will vote, but with a weight. Each model has a different importance. Or models are not all equal in their voting. It's not a pure democracy. So one model can have more say than another model. And this importance is based on their accuracy. How did they perform during the training? When we constructed them, how many they got right. So each model will have like an importance score based on how like samples they classified correctly. Are you happy?
Yes, so that means the sample that has a high weight, that means they are not good or what? Like, because if they have a high weight, we repeat. Yeah, high.
Sorry?
If they have a high weight, that means we double it, or we double their weight because they didn't classify well.
Okay, we have two scores. We
okay.
have a score for the model and the score for the sample. It's two different things. It's two different things. A score for the model and the score for the sample. And these are two things, two different. The score of the sample is of the example on the data set. This one. So we have here my samples. So they have a score. This score is used inside the model. And then when we construct a model, this model has its own score, its accuracy score. This is importance score of the sample, and this is accuracy score of the model. They are two different things. Okay?
Yes.
Let's see the next slide will explain it better. Yeah, this is like an example, a visual example. So let's say we have this data set, plus minus. So we have two classes, and how many dimensions? How many dimensions do we have?
Two.
Two dimensions and two classes.
Yeah.
So what we do, initially they are all the same. They have all the samples have the same weight. They have the same importance. We don't see that one sample is more important than the other. So what we do, we build a first classifier. This one, we'll take this original data set and we build a simple decision tree with one level. So it will just divide it by, you see that decision trees divide things by vertical and horizontal lines. So this one decided to divide things in here. Which ones are misclassified now?
3 pluses.
Yeah, these ones are misclassified. So what happens now? We give them more importance. So we built a model here, and we give these 3 more importance. So we go in here, and you see that they are bigger. It means just for the notation, we are giving them more importance. They became bigger because we got them wrong. Now, well, because they are more important, the new model will divide things in here. Now, what do we have wrong?
The 3 minus.
The 3 minuses. This is the wrong. Now we give it more importance. And this model will divide things in here. Again, it made this mistake, and this mistake. If we decide to stop, averaging these models will correspond to this. So each one of them, so how many mistakes did this model make?
3.
And this one?
3.
And this one?
3.
Yeah,
3.
so because of that, they will be all equal. This model will have the same vote as this and this. That's why they are all equal. They have the same voting power because they make the same number of mistakes. And when we combine them together by this voting system, we will get a classifier like that. How many mistakes do we have here?
0.
Nothing.
We got everything right. We got everything right when we combine them. We combine them by vote. So this region is blue in 2 cases and red, a little bit red in here. So this zone will be blue because we have two blue and one is saying this zone is red. So this one will be blue. Okay?
Yes.
The voting said that. Same with here. Not same. Here they all agree that this is blue.
Blue.
And here we have 2 blue, this zone, and 1 red. So we take the blue. Here we have 2 red and 1 blue. So we take this as red. So this is the voting. They are voting by majority because they are all have the same importance. Same goes in here and same goes in here. Here we have 3 reds, so we have a full agreement that this is red. And here we have 2 red and 1 blue, so this will be red. The voting makes this model, this final model. And this is very generalizing, general model with a 100% accuracy, if you can see. The generalization power is very high. It's like it is classifying things continuously. It's not like doing this is blue, this is red, this is, and trying like to mix and match these places. It's like fully continuous, simple, as you can see, like 2 regions, just 2 regions, and it's getting 100% accuracy. Another example now with weights. So we have this first data set. We build a classifier, this one, and we see what mistakes we made. So this is a kind of error rate. And this is the importance of the model. This is the importance of the model. We can compute it by many means, this importance. There are multiple formulas of doing it. So we have this, and based on this error, we compute this importance. Now, in the new data set, these 3, the misclassified one, are the most important. Again, this model will do this. It computes some sort of error and an importance score. And these are the 3 when we made a mistake. So here they are given more importance again. And we have this final data set, final classifier with this score, importance score, and some error score. So we end up with something like that. And the final classifier, we multiply the importance by the outcome. So if we have a new sample coming in, we take this new sample, we put it through all the 3 classifiers, we get the results, and the voting will depend on the results, of course, but also the importance. This model is more important. This is a little bit less, and this is not super important. And then, so we multiply them and combine. Here, H1 is the prediction of each model, H1, H2, H3. And here, just to make it simple, it's the prediction is negative if the class is negative, -1, or +1 if the class is positive. So we take the sign. So if this one is positive, and we multiply and do the sum, we see the sign, and this sign determines the class. It's rather simple. Don't like see it super complex. Are you happy, guys?
Yes.
Yeah.
Happy with this? It's a voting system. We create models that are sequential. Each model depends on the outcome of the previous one, where like the new data set will be constructed based on the error of the previous one. And we continue creating model after another until we got a series of models, and to combine them, we combine them this way. We multiply their score, importance score, by their prediction. We sum and we take the sign. So this model will have more say, because it's more important. And as I said, the importance of the model is different than the weight of the sample. The weight of the sample is here and here. The importance of the model depends only on the score, on the accuracy score of the model. Okay?
Yeah.
Perfect. Another example. This is a decision tree, a full decision tree. And these are what we call the stump. Yes. These are the stump. Generally, at each level, we take only one of them, the best one. The same way we construct a decision tree. It's so small, you see. For adaptive boosting, we use stumps of this level, very small. Just one variable, and then we combine them later. And by magic, it's like impressive. It gives impressive results, really impressive. This voting mechanism of because each one of them is highly general. Classification on training and testing will be almost the same for all of them. And combining them by vote doesn't deteriorate this aspect. It just improves the accuracy. It improves the bias, but doesn't reduce or doesn't make worse variance. So this is another example how this works. So for example, in the beginning, we take this stump. We found that age is the best feature to split on. So we use this stump. We see what samples we got wrong. We give them more importance and construct a new stump. We found out that this attribute is the best one to use. We compute its accuracy, the number of errors, give these samples where we have more errors higher importance, and do another thing again, another stump again. And we do a fourth one. The only thing we don't know where to stop, because we can still use the same variable twice. There is nothing preventing us from this. We can use this many times, the same variable. For example, say in here, if we find that age is still the best variable to split on, we use age again. So each stump is more or less independent on how it is constructed. It just the data set are not independent. How we construct each data set. So this data set that comes here will depend on the outcome of this. And so that's why boosting will focus always in the samples that were misclassified. This is like the rule of boosting. Bagging will always doesn't focus, it just produces banks of data sets independently of each other. But boosting will produce the next data set based on the error of the previous model. So that's like the base of boosting.
So, Reda, are we trying to improve the model when we just take the previous misclassified
exactly,
data?
yes. We want to improve the bias. Exactly.
The bias, yeah. Okay.
And we are using very general models. So small trees are always super general. Highly general trees. And we are improving their bias when we combine all the models. And we don't lose the accuracy or this good variance. The low variance, we don't lose it. This is like the magic of boosting. It improves the bias without losing the variance, which was, like I said in the beginning of the session, this is a trade-off in most models. But with ensemble methods, we can make this trade-off better. We can improve the trade-off. Okay?
Yes.
No, now, let's see the formulas. The initial weights of the samples is something like that. 1 divided by n. N is the number of samples. Because they are all the same. They have the same weight. Okay? Are you happy with this? This is the weight of the sample. The samples are all equal in the beginning. So that's why each sample's weight is 1 divided by n. N is the number of samples. So they take each the same amount of importance. Okay?
Yes.
Miriam, are you happy?
Yes.
You asked me about this. And the importance of a stump is this formula. Half logarithm of 1 minus the error. Error is just the number of cases that we got wrong divided by the total number of cases. So the error rate divided by the error rate. So this is the importance of a model. It depends only on the errors that we made. So we have the weight of the sample and the importance of the stump. And the importance of the stump here is the graphic that depicts how it works. So the more error we have, the less important alpha it is. So the more error we make, a model makes, the less important this alpha is, this model is. So we are going negative. And the less error we make, the higher we go. Okay? Which is normal. Are you happy, guys?
Yes.
Yes.
Yeah. So that's as simple. This importance. And the new sample weight equals this. The old weight, its old weight, multiplied by exponential plus minus alpha. We use sometimes plus or minus, I think, depending on the class, on its class, if I'm not wrong. So we multiply it by some rate. So, and so those that we got wrong will be increased. I think the plus is for the one that we got wrong, and alpha is the importance of the stump that we had before, that we have created before. So here, this is the update of the new weights. This update. Okay. So each time we update all the weights of all the samples based on this formula. The old weight multiplied by if we got it right or we got it wrong. So if we got it right, this will decrease. If we got it wrong, this will increase. The weight will be higher. So for the plus and how, and of course, if we made a lot of mistakes, this will be lower. Okay.
Yes.
So these are just the formulas. If we got something right, its weight will decrease. If we got something wrong, its weight will increase. This is just what we want to do. Now let's analyze this model a little bit more. In practice, this is how. So here it's the number of samples around. Rounds is means that how many samples we are constructing. In the beginning, we are constructing the first sample or the first model, second model, and we keep going. We keep creating more and more samples, more and more weight of percent samples. Oh, sorry, more and more models. We are creating more and more models. And with the more models we create, we can see that this is the error on training. This is the error on training. And the more model we have, the error is shrinking. Do you agree with me? Do you see that? The more models, the more the error on training is shrinking. But this is there is something, another thing that is strange, guys. Something that is strange here. Give me 1 second, guys, to close the window. I think these guys are. Okay, so you can notice here something strange going on. Can you tell me what it is? Here we reach 0 very quickly in terms of error on training.
Yes.
And here we are not improving anymore. Yes or no? Here we are not improving.
Yes.
Yes.
But this is improving, which is really odd. This is not improving. We are adding more trees, more stumps. This is not improving. Like the thing, like the intuition will tell us to stop at 10 or so. But this is not. This is like improving, even though this is not improving. This is really strange in machine learning. You can see that this is improving the more we add the stumps. We are generalizing even better.
Mm-hmm.
Yeah.
Which is it means we are even improving the variance at the same time. Initially, we wanted to improve even just the bias. But the more we add, the more the variance is improving. Here we have like an acceptable variance, more or less. They are not too different, 0 and 10. They are not so different, but just because we don't have 100 here. But they are very close. But here it's still improving.
Mm-hmm.
The test error decreases even after training error reached 0. More weak learners, more complex hypotheses. How come we are not overfitting? The more, of course, the more weak learners we are adding, the more complex the model is becoming.
Yeah.
True.
But we are not even overfitting. You can see that clearly we are not overfitting here. We are getting, test is improving. Why? This is the reason, kind of. There is a lot of research going on to understand why it behaves like that. Adaboost keeps increasing the margin in the voting. When it starts voting, like the voting system, we increase the margin of between classes, even after it has managed to classify all training examples correctly. So it keeps learning how to make a better vote, even after like all the training examples are classified correctly, because there is no stopping criteria. Like there is no criteria to stop. The more we add, the more the margin of the number of yeses and no is becoming better. So if, for example, we have we have, for example, say for one case, let's say we have two classes. We have 10 yes and 9 no. Well, what class will be this? Let's say that their importance is the same of all the models. So we have 19 models, 10 are yeses and 9 are no. So what class will it be?
Yes.
Yes. But the more we add, the more the margin will get higher. So if we are at 90, if we go to 100, we might end up with 70 yeses and 30 no's. Which means the margin, you can see that the difference between yes and no became higher.
Like the weight?
It's like the margin. You can see it as some kind of margin of the SVM or something like that. We are making, we are getting a higher confidence on the vote. The confidence here is small, 10 to 9.
Yeah.
But here it's much higher, 70 to 30. So that is what is happening when we add more stops. Like this confidence, this confidence zone is getting better and better and better. And that's why we are making better votes. Okay? That's why we are making these better votes. And this is getting better. We are going, this stopped, but this is getting better because better votes means here seems better generalization. Okay? It's really nice to see this strange phenomenon happening, like unexpected. Really impressive, don't you think?
Yes. How do you keep learning when you already know everything? Like
yeah. How can you keep learning when you think you know everything and you still keep learning without realizing it? The model, because the model doesn't see this, it sees only this. It's just like having like a bigger confidence on the voting system, and it is becoming better. And it doesn't overfit, like you can see. Overfit means that this is 0 and this goes here. This means overfitting, but this doesn't overfit. This is the strength of boosting. It's really, really a powerful method. And it is considered, especially gradient boosting, which is another version of boosting. It has a lot of similarities with Adaboost, but if you go to Kegel competitions, it's the king classifier. The gradient boosting is the king classifier. I wanted to do it today, but we won't have time. We will do it tomorrow. It's some variation on Adaboost, not different from it. It's the same boosting, but with a different way of creating the new sets, new data sets. So the strength of Adaboost. It has just few parameters, actually, just the number of stumps. It's simple to implement, implicit feature selection, because it uses decision trees to select what features to use. Resistant to overfitting. You can see that it is quite resistant to overfitting. It has a low bias and low variance. Perform very well in practice. When we use it, it performs very well. Its weaknesses needs a termination condition. It's not easy to know when to stop. There is no like a clear rule to say when do we have to stop. It is also the biggest weakness. It's that it is sensitive to noisy data and outliers. If you have many outliers and sensitive data and noisy data, then the results can be bad. And we can must adjust for cost sensitive or imbalanced class problems. So yeah, if we have an imbalanced data set, we must adjust them. And it doesn't support multi-classes out of the shelf. There is some adjustment used on it to make it multi-class. But it's big. All of them are, I would say, okay. We can always correct these problems. But this is the bad point. It's sensitive to noisy data and outliers. If our data has a lot of noise, then Adaboost cannot be the best method to use. So thank you. That was today we had a short session on Adaboost. Any questions, guys? Any questions?
Fine. Thank you, Reda.
It's clear?
That's okay for me.
So
And in
far,
the
good,
past,
yeah.
perfect. In the past, I think before the emergence of gradient boosting and things and other methods, it was like considered as the best classifier out of the shelf. That's how it was labeled. The best out of the shelf classifier. It's so simple, but it has like this strong properties. So we are really close of completing the classification chapter. Next time we are going to see the gradient boosting and just to wrap up everything we did, or to see again all the classifiers, their strength, their weaknesses, everything about them. We are going to revisit them and compare them. So thank you for your attention, guys.
Thank you.
And see you next time.
إن شاء الله.